Hello everyone and welcome to today's webinar, PCOR-SIMS Analyses of Gallium Arsenide pHEMT and Gallium Nitride HEMT. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted, however, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Charles McGee, Chief Scientist at EAG Laboratories, will be answering some of the questions during the presentation, and we will also collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce Tamel Buyuk-Limanli, Scientific Fellow at Vice President at EAG Laboratories.
Good morning, good afternoon, and good evening. Today's seminar will be on device analyses using PCOR-SIMS, specifically high-speed electronics, pHEMTs and HEMTs. And we'll start with a bit about me. I have got my PhD in material science from University of Florida. And since then, I have had many years of experience in surface analysis, specifically SIMS. I joined EAG in 1994, and ever since then, I have spent most of my time in secondary ion mass spectrometry analyses and development. I have worked on several methodology improvements to device analysis, specifically compound semiconductors. And we're going to show a few examples of those today. So let's start with a simple description of how the secondary ion mass spectrometry dynamic SIMS works. This is a simple schematic of the instrument. We have a ion source that is injecting ions into the sample of interest, and that in return sputters species or particles from the sample, either ionized or neutrals. The ionized particles are extracted by applying electric field, sent into the mass spectrometer or mass filter that is designed to allow a certain specific mass to flow through into the detector. We can sweep the mass filter and get a mass spectrum, or we can keep the mass spectrum and sweep the beam and collect the information and form a map of a specific mass or masses, or we can have a profile of these specific elements or masses as we drill into the sample, and we call that a depth profile. The dynamic SIMS most common mode is the step profile, and this is what we'll be looking at today. So let's look at, in an atomistic schematic, what happens in a sputter process in secondary ion mass spectrometry. You have a primary ion beam hitting a crystalline structure made up of monolayers of atoms, and this momentum transfer mixes the atoms in material of interest to a certain mixing depth, and this mixing depth is directly proportional to the momentum or the kinetic energy of the incident ion. The higher the kinetic energy, the higher the mixing range. This mixing range controls the depth resolution. Minimizing the kinetic energy of the incident ion increases the resolution of the SIMS in the depth profile mode. And we're going to see examples of that. The trouble is that you need to find a balance between getting a good depth resolution or getting the analysis done in a effective manner, or get this detection limit you desire. They all work against each other. So you have to design the SIMS instrumentation or measurements based on the specific goal. So this incident ion mixing the material and ejecting atoms or sputtering the atoms, or they form moleculars, come in as positive ions or negative ions or neutrals. The ions that are sputtered off are called secondary ions, and hence the name secondary ion mass spectrometry. But the difficulty in SIMS is the formation of these ions with respect to the molecular or atomic neutrals changes from one matrix in the sample to another matrix. This is an example of a boron implanted silicon material. We're plotting the silicon intensity. We're looking at a secondary ion intensity. And in the bulk of the silicon, we have a flat silicon line. But as we approach to the native oxide, as all silicon samples has, the silicon intensity goes up. But we know in SiO2, the native oxide, we have only 1/3 of the silicon atoms than we do in the bulk. So this illustrates the difficulty and the challenges in quantifying the SIMS intensities. It is going against what you would expect. When you would expect that the intensity of a given ion will decline in proportional to the concentration. But in this case, we're seeing that the intensity of the ion is going up by a factor of 10, in fact, when the concentration is only 1/3 that's in the bulk. In this particular case, we want to quantify the boron. So if silicon is doing that, we don't know what boron is doing. So to give a properly calibrated boron concentration, we really need to understand what is going on here. So in SIMS, this problem is resolved by running standard materials that has the species of interest in a matrix that you want to quantify. In this particular case, having a boron implanted in SiO2 and implanted in silicon will allow us to quantify boron in both of these matrices, even though the intensities are not making sense. The formulation for doing that is quite simple. The relative sensitivity factor is calculated from the standard material that I just described, and you multiply it by the intensity of the species of interest for data point I, in this case, the boron intensity, and divide it up with the matrix intensity. In this case, it was silicon for data point I. And this formulation gives you the concentration of the element of interest, in this case, boron, at data point I. But one of the challenges in SIMS is only a few percent of these sputter particles are ionized. And this is, as I was describing in the previous slide, controlled by the matrix. And because of the strong effect of the matrix to the ionization, you must have a proper standard so that this RSF is relatively accurate and it gives you the proper calibration of the species of interest. The other dimension of the profile is the horizontal axis or the depth axis, and that is done by calculating a sputter rate or the etch rate of the measurement by measuring the total depth and dividing it up by total analysis time, and using that rate multiplied by the timestamp at data point I gives us a depth in data point I. However, as we were describing, matrix has strong effects on the relative sensitivity factor. It also has an effect on the sputter rate. And this becomes a big issue in a compound semiconductor structure because more often than not, compound semiconductor materials have lots of different layers with different compositions and sometimes graded compositions. So the starting point of our presentation is that one of the challenges for SIMS quantification is minimizing the matrix effects. For compound semiconductors, there are other issues that the engineers that we work with over the years have asked us to improve. Traditionally, the SIMS was used to measure the dopant and impurity concentrations only, and in usually a single matrix like gallium arsenide. But over time, the compound semiconductor layer structures became very intricate, and changes in gradients in the composition has become very important. The customers, our engineers who are working on epitaxial gallium arsenide or gallium nitride development, wanted to measure the dopant gradients as accurately as possible. As I was describing in the depth resolution, this became an important factor that we needed to consider. And to be able to do troubleshooting or doing a development of a growth of a structure, precise location of a dopant or impurity element has become very important, and we'll show you examples of that today. Over time, the success of the SIMS have led the epitaxial engineers to request quantification of major elements, which back then was not expected to be done with SIMS, as they thought was that SIMS is not a good method to quantify major composition. But having done the research on it, we came up with methods where you can actually quantify the alloy compositions in compound semiconductors at every data point for group 3 atom fraction or group 5 atom fraction, and especially for very thin layers, for example, at an in-gap etch stop. And one of the other things, especially in photonics, is the gradients of these group 3 and group 5 elements, and see if SIMS can actually help out with the shape of these composition gradients, which you cannot measure with any other means as easily as SIMS can. But when you're measuring the dopants in SIMS, accurate layer thickness is very, very important for you to determine the distribution of a dopant especially in a very thin layer. And all of that, these requirements that came to us with our epitaxial engineer partners or customers, led to the new method we call PCOR-SIMS. And PCOR stands for point-by-point correction of sputter rate in the RSF changes that we talked about in 2 slides before in the formulation. So instead of having a constant number for relative sensitivity factor or a sputter rate, we have a varying values that gives us the most accurate depth and concentration at every data point, and we call that PCOR-SIMS. How do we get there? Is essentially not that difficult. You develop a calibration curve for a variety of matrices, looking at the elements or dopants of interest. So in this particular case, we would implant substrates of interest, let's say arsenide or AlGaAs compositions or AlGaN compositions with known amount of dose, and an assumption is that the dose of the implant is the same in all of these species. So any variant in the intensity in the SIMS will be a matrix effect, and the hope is that we develop a calibration curve of that intensity with the known concentration for each of these AlGaAs compositions. One such calibration curve is for carbon and silicon, and we're plotting the sensitivity factor with respect to change in aluminum content in an AlGaAs. So this is the gallium arsenide RSF, and this will be the aluminum arsenide RSF. And as you can see, the change in carbon RSF with the change in aluminum content is almost linear and similar in silicon. And what is most important is the matrix effect. If you were to use the gallium arsenide sensitivity factor to quantify carbon in, I say, 80% AlGaAs, which you would find in VCSEL structures, you'll be making close to a factor of 3 error. So this is now very important for calibration of carbon and silicon or other species of interest, to be able to measure these dopant concentrations as accurately as we can and independent of change of matrix composition. Now let's show an example of what happens in actual samples. This is one of those samples that we showed 2 slides ago. It's an 80% AlGaAs implanted with carbon and silicon and tellurium and all that. And in this particular case, we're looking at the carbon and silicon implant. And now we're plotting it in concentration, atoms per cubic centimeter, and it is plotted using a gallium arsenide RSF. When you calculate the dose of this implant, we find that the dose is factor too low. But we know that from the previous slide because the sensitivity factor of carbon in AlGaAs is factor too low. But when you do a point-by-point calibration using the curve, even at this interface where the AlGaAs is changing, we get a profile shape that looks like this. And when we calculate the dose in these we find that it is exactly the same dose we had in gallium arsenide. So this gives you an idea of using PCOR-SIMS or regular SIMS and how much error there could be in the change matrix elements. But in dynamic SIMS, there are two dimensions, and there's a horizontal axis, which is the depth axis, and you need to have that depth calibration as accurately as possible so you can actually measure the dopant thicknesses correctly. And as I pointed out, the sputter rate varies with the change in composition, especially in gallium arsenide or indium phosphide, all these compound semiconductors where you have different layers. And with similar to the RSF, we can develop a calibration curve looking at the sputter rate ratio from gallium arsenide to AlGaAs plotted against the AlGaAs composition. We have a calibration curve that we use, and based on the measurement of the AlGaAs, we can measure what the sputter rate need to be from this calibration curve. These calibration curves are not always linear, and it's not always easy. In an AlGaN structure, it's actually a nonlinear distribution as you switch from gallium arsenide to aluminum gallium nitride. But having the curve, we can actually determine what the etch rate is for a given AlGaN composition. But this all depends on measuring the composition at a given data point accurately. And as I was describing before, back 25 years ago when I started doing SIMS, SIMS was not considered to be a technique to use for measuring composition. But over time, because of the demands of our customers and the epitaxial engineers, we looked into developing it. And there were, at the time, a lot of studies in the SIMS community to measure AlGaAs compositions, and several articles got published in quantifying AlGaAs in aluminum to gallium ratio. But it required that you have a reference material. And for a long time, the lack of AlGaAs reference material made it very difficult for us to confirm our results. But about 10 years ago, well, now it's 14 years ago, National Institute of Standards and Technology issued a reference material 2841 to an accuracy of 0.0014, and you were one of the first ones to purchase that. So that gives us a basis of quantifying aluminum as a NIST traceable measurement. But this is only for one composition, and we need to confirm that our measurement, our method of quantifying aluminum is correct for all the aluminum concentrations. For that, we usually use a Rutherford backscattering or RBS measurement. This is a reference material where we have concentrations of 7 atom percent aluminum and 80% aluminum. In this particular case, we're basically measuring gallium to aluminum ratio and assuming that arsenic is 50%. And this is the SIMS measurement, and all these numbers were compared with the RBS measurement for each individual layers, and we find that the SIMS quantified using PCOR-SIMS method measures this aluminum concentration within 5% of the RBS measurement, which is actually the uncertainty of the RBS measurement anyway. So this gives us confidence that we can convert the secondary ion intensities into composition, and we can make it NIST traceable. However, precision or reproducibility is different from accuracy. You need to be able to do this from one sample to the other sample, and from reference material to the sample of unknown. So you need to convince yourselves that the SIMS intensities or calibration is consistent from one measurement to the other measurement. In SIMS, what we do is make the measurement twice or 3 times or 4 times to get a statistical deviation. So here's an example. This is a calibration run for an oxidation layer in VCSELs, where the customers, the engineers, VCSEL engineers, are varying the aluminum concentration to control the oxidation in the aperture layers of the VCSELs. In this particular sample, the customer is trying to design a vexil structure that has 99.3% aluminum versus 97.5% aluminum. These two different samples. The difference between them is roughly about 2 atom percent. And the question is, can SIMS measure a 2% difference in aluminum in these two samples? And when we repeat the measurement, we actually find that for AlGaAs, SIMS intensities are very, very reproducible, very, very precise. You can even see the undulation being reproduced very clearly, and the precision is less than 0.5%. So that gives us the confidence that we can measure a 1.8 atom percent difference between samples. And if it becomes an important issue in any structure, it could be a pHEMT structure, it could be an HPT structure, it could be a vexil structure. SIMS is a very reliable method of measuring aluminum concentrations in the AlGaAs materials. That doesn't necessarily mean all compounds can be measured with this precision or accuracy with SIMS. It's just that you need to do the study, the proper study, to see if it is possible or not. So armed with the ability to quantify the matrix composition, having the calibration curves for being able to do the measurements, gives us confidence in intensity calibration. But let's look at the confirmation of the accurate depth layers. So every data point requires a separate sputter rate, as we have seen in the calibration curves. Once this is applied, do we get the correct layer thickness? Here's an example. This is a DBR layer of a vexil structure using an average sputter rate, which is done in routine SIMS, or with PCOR-SIMS, where you actually vary the sputter rate at every data point. And as you can see, there's almost a 20 nanometer difference in each layer here. But as with the intensity calibration, we need to confirm these layer thicknesses to be accurate. In our rule of thumb or metric for layer thickness accuracy is transmission electron microscopy. And let's do an overlay of a pHEMT structure that's calibrated using PCOR-SIMS, and then the same sample measured by TEM. In this particular case, we know that aluminum is causing a change in sputter rate from gallium arsenide into aluminum arsenide. And in indium gallium arsenide, the sputter rate is actually increasing while AlGaAs is decreasing. So there's a big change from here to here, could be more than factor 2. But yet, when point-to-point corrected depth scale gives us a profile of SIMS that matches the microscopy thicknesses, as it is very clear here. But SIMS inherently, because of the atomic mixing, as I showed in my third slide, we cannot measure anatomically sharp interfaces. That needs to be done in atomically resolved electron microscopy to really see the sharpness of these interfaces or in the superlattices. SIMS in this particular case is giving you an idea or a method to compare from one sample to the other sample. And more importantly, in the pHEMTs, these planar dopants or the delta dopants around the in-gas channel region. And we're going to see a lot more examples of that. So let's jump into the pHEMTs. Now, you need, for pHEMTs, because of the planar dopants that are only 2 nanometers, you need to have the proper depth resolution. And we described that in the atomic cartoon. We were showing you the sputter effect. Now, this is an example of 2 samples of oxide. And in sample 1, oxide is grown in an N2O ambient. And in sample 2, the SiO2 grown SiO2 layer is treated by N2 plasma. And these 2 samples actually put the nitrogen in 2 different places in this oxide. In an oxide that's grown in N2, puts the nitride layer at the oxide silicon interface. Whereas if you treat the oxide, grown oxide with N2, it puts the nitride on the surface of the oxide. Now, the key here is the depth scale. Notice that these are only 1.5, 1.4 nanometer oxides, we're talking about 5 atom layers. And yet, with proper SIMS protocols or high depth resolution protocols, you can see the distinction between a nitride on the surface versus nitride in an oxide when you have only 4 atom layers or 5 atom layers. So that gives us confidence that now we can look at pHEMT structures where you have a few monolayers of silicon delta layers. So this is a boilerplate pHEMT structure, and there are 2 main important layers that epitaxial engineers are looking at with SIMS. It's the epitaxial and substrate interface impurities. The concentrations of these are proportional to the leakage current, so you want to have a better control, better concentration measurements, and obviously the need to minimize them as much as possible. The other part of the pHEMT structure is where the electrons are moving left and right, the Schottky region, the channel region, the delta, silicon delta, around the InGaAs channel region, and impurities that are present right where the electrons are for electron traps, etc., and impurities in the superlattice, InGaAs superlattice buffer. So the first, we want to look at the epitaxy substrate interface impurity analyses. Please note that this is essentially 1 or 2 monolayers of an impurity at the start of a epitaxial growth. So if you really want to do a reliable measurement of these impurities, you have to prove yourself that the SIMS had the ability to measure these with a certain precision so you can make comparisons. So as I've shown before, the way we do that is making a measurement in close proximity of each other in a given sample to determine a statistical deviation. So we take a wafer, say that you're interested in the distribution of these impurities at the episubstrate interface across a wafer, you would make a measurement, say at the center, a number of times in a sequence of measuring it at different edge points, and compare the edge point measurements to the center of measurement that's repeated. The center measurement or close proximity measurements assumes that the concentration of these impurities are the same. So this is an overlay of 4 measurements at the center of a pHEMT wafer, and we find that the integrated concentrations are measured with a standard deviation of 3% or 6%. So one would say that when you make the measurements at the edges, and if the concentrations are more than 3% or more than 6% different from what we measure in these center measurements, that would be considered real. So when you plot that across a wafer, so that 4 corners of the edge pieces versus 4 measurements of the center, so these are the average concentrations measured in the center, and the 4 data points are plotted right at the center here. And as you can see in the oxygen case, in this axis, we see that the oxygen concentration at the episubstrate interface is much greater than what we measure in the center. So using this method, you can do a study of how the impurities in a given structure, even if it is only 1 or 2 monolayer thick, reliably to a degree of 5% or 6%. But over time, most of our engineer customers wanted to have a more intricate study of the channel region. So we needed to measure these delta dopants in great depth resolution with accurate concentrations from InGaAs to InGaAs, etc. And the point was to be able to measure the spacer thicknesses. So this distance from the peak of the planar dopant into InGaAs determines the mobility in this transistor. And the total concentration or integrated concentration of this delta determines the electron charge density. So we needed to have the proper measurement to be able to do these measurements for the people who are developing pHEMT structures. And we need to confirm that this difference in spacer is actually proportional to the mobility of the transistor. We're looking at a set of pHEMT structures having a different spacer thicknesses. pHEMT A has a 4 nanometer spacer from the peak to the in-gas interface, whereas pHEMT B has only 2.5 nanometer to that interface. When we compare the mobility of these two data points, so here's A and here is B, we see that the spacer layer directly proportional to the SIMS spacer layer thickness measurement. So this gives us confidence that if one has to study the effect of the spacer to the mobility, you can use SIMS at high depth resolution to be able to design new structures of pHEMTs. But as the electron mobility is improving with higher and higher layer thicknesses or thicker spacer thicknesses, you would need more electrons to go in, and then you need to correlate the total charge density that we measure by SIMS with the active charge density in electrical measurement. As you can see, we can see that the measured silicon areal density is proportional to the charge density. But as you put more and more silicon dopant, we find in the past that sometimes it causes a broadening of the silicon delta, spilling over to the Schottky, and then causing a lower breakdown voltage because it's this resistivity has declined. So can that be used to troubleshoot a 2 pHEMT device? Now here's an overlay of 2 pHEMT devices. One is considered to be a good pHEMT, and the other one considered to be a poor pHEMT. And the high depth resolution of the pHEMT device analysis overlaid clearly shows that the poor pHEMT, the silicon delta dopant is spilling over to the Schottky and reducing its resistivity and causing a lower breakdown voltage. And this was exactly the effect that the device engineer was seeing in the wafers that he received, and SIMS was a big proof of how the wafer development or wafer growth has led to this low breakdown voltage. You can obviously do the electron mobility study with respect to by using the spacer thicknesses or measuring the total silicon concentration to get to the charge density. Here's another example of how this SIMS method, this PCOR-SIMS method with high depth resolution, can be used in development of pHEMT structures. This is a structure that's grown where the Schottky is grown at different temperatures. And as you vary the temperature, you see the shape of the silicon in the Schottky region is changing. The important fact here is that as you change the temperature, it only changes the silicon profile shape in the layers above, not at the bottom. In other words, the change in temperature is not a diffusion mechanism, because if it was a diffusion, you will see a symmetrical distribution of the silicon, and we see no effect in the silicon delta layer in the bottom. So what we can conclude from the study is that because of this asymmetry, the silicon appears to be segregating into the upper layer when the temperature is higher and higher. So you would want to use a lower temperature to keep the silicon intact and not spill over to the Schottky region. So with SIMS, you can have a clear understanding of how to grow these structures. So there are other elements we measure in the SIMS to really understand. We've done several studies of pHEMT structures, and usually some of the elements are pointing to the reactive memory contamination. Some other alkali contaminations we measure in these pHEMT structures lead to other contamination issues. The point is, depending on what impurity we find at what location, we can make a suggestion of where the source of the contamination is. So I would highly encourage anyone who's having some issues with their PM structures to do this kind of an impurity study to really pinpoint what is happening in a failed pHEMT device. Now let's move on to the nitrides. Nitrides are a bit more challenging than arsenides because the epitaxial quality is not same as the arsenide materials. We end up having a lot of defects in them and different kinds of defects. And these defects affect the quality of the SIMS measurement. Since in SIMS we don't image the cross section of the material, some signals we see in SIMS might be an artifact of these defects in the material. So I'll give you an example of it. In GaN HEMT structures grown in silicon substrates, we have a lot of defects. You grow all these buffer layers to absorb most of the defects. So by the time you get to the layer of interest where all the action is, you have minimized your defect density, as this electron micrograph shows. But sometimes you end up with these defects that creates a pit on the surface. And when you're trying to make a measurement of this top layer of interest, these pits create a fictitious curve or fictitious concentration that may lead you to have an incorrect assessment of your material. Now let's look at that surface from top down. This is an AFM image. All these little spots are the pits in the surface. And if you look at it from the cross section, these pits can be as deep as 45 nanometers. And when you're trying to make a measurement of, say, carbon in the top 20 nanometer region, as you're profiling down, and these pits have all these carbon contaminations from air exposure, when you break into it, you'll still be seeing carbon, and you might be thinking that it's a carbon diffusion from the surface in these layers, but in reality, it's an artifact of these impurities in these pits. And what we do is we basically do a cleaning of these pits so we can get a correct profile of the carbon even in the top 20 or 30 or 40 nanometers in these HEMT structures. And if you would do that, you would have these long carbon tails coming from the surface. That's usually proportional to the depth of the pit. So armed with this knowledge and cautious, let's dive into the gallium nitride HEMT structures specifically grown in silicon substrates. And it has many layers into it for many functions to it. And what we find over time is the defect density in the buffer region is one of the issues that you need to be working on, and that leads to a lot of microscopy measurements. And the contamination in these buffer layers are causing leakages in the GaN HEMT devices. So measuring these impurities in these buffer regions is quite important. And just like the pHEMT structures, GaN HEMTs also have a very thin layer at the very top that requires a low detection limit impurity measurement or a dopant measurement in very, very thin layers. So we'll show you examples of that. Here's a plot of a gallium nitride HEMT structure grown in silicon substrate. And you have all these aluminum nitride and algan materials for nucleation, and then buffer regions to reduce the defect density. And this is a measurement of carbon, oxygen, and silicon, which is the most common measurements we do in gallium nitride HEMTs. So you have a region where we look at impurities in the buffer region, and we have another region that we look at for TrueDAC. Why do we want to do PCOR-SIMS just like in the arsenides? The carbon RSF changes from gallium nitride to algan by a factor 2 or more, depending on the algan composition. And if you were to plot, say, carbon concentration using a single RSF, you could be making a mistake of factor 2. So if you want to compare your carbon concentration again, with respect to carbon concentration in the algan, if you don't use PCOR-SIMS, you'll be making an inaccurate assessment of your GaN HEMT structures. So we basically recommend everyone to use PCOR-SIMS from GaN to algan so that these concentrations are quantified accurately at given data point, independent of the stoichiometry. And when you have that, you can do the center and edge comparisons, just like in the pHEMT structures. And you have to have very low detection limits in these regions because they're intentionally undoped. But because of the epitaxial growth, you need to you may end up with some impurities. We can have silicon detection limits in the E14s and hydrogen in the E16s. That this is a real hydrogen concentration. We do a lot of metallic impurity analyses in these materials. Here's an example of boron, iron, moly measurement, and here's an example of magnesium is intentionally doped at E15, and because we have a E13 detection limit, we can clearly measure E15 level magnesium. So you have to have the proper metrology to be able to measure these E15 level concentrations as accurately as you can. So this is a detection limit of all the impurities that we measure in gallium nitride material. And as we measure all these things in gallium nitride HEMT structures. But as with the pHEMT, there's this top layer where all the action is. And you're designing all of this for the benefit of this very thin layer at the very top. In this measurement where we do 4 micron profile, as you can see, you cannot make out anything at the top. This is a 30 to 40 nanometer layer, but because of the high kinetic energy of the incident ion, so we can make this measurement in a cost-effective manner, you get almost no information at the top. What do we do? As we described in the second slide of the webinar, you have to reduce your kinetic energy of the primary beam hitting your sample, so you get a better depth resolution in this region. So when you do that, you can actually get a profile within the top 20 nanometer or 15 nanometer here, as we have shown in the oxynitride gate oxide example. And this is a linear plot of the same thing. You can do a study of the carbon linear aluminum and gallium and logarithmic carbon. You can see the GaN cap layer clearly. You can see the algan layer clearly, and you can see the aluminum nitride layer clearly. And you can basically look at the carbon concentration with respect to change in aluminum concentration with PCOR-SIMS as accurately as anyone can do. The key here, to be able to measure the carbon concentration in the E17 layer level in such a thin layer, you need to have the proper protocol so these carbon on the surface is not really having long tails and obscuring what you try to measure. And when you have that protocol, you can actually do a comparison of a wafer center with a wafer edge. This is the wafer center measurement. But when we do the same measurement with same high depth resolution and good carbon detection limit in the top 30 nanometer, we see a big difference in carbon in that channel region between the center and the edge. And it's factor 2 higher in the algan. And in the edge, we are having these carbon peaks, especially near the to that region. So just to show you an example of proper SIMS method can actually give you very intricate, detailed measurement of these very difficult samples to be measured. You just need to make sure that you apply the most appropriate SIMS measurement. And we can even do iron measurements in these very thin layers. So essentially, in summary, SIMS is a very good method to measure very low concentrations, dopants, and impurities, but it can also measure high concentrations to atom percent. So from parts per billion to percent, dynamic SIMS can help you out. It can detect all the elements, including isotopes, and most importantly, hydrogen that is found in all the epitaxial growth in compound semiconductor. And you can get a layer structure as we've been looking at it. So it's a very powerful tool to do thin film analyses for dopants and impurities and get an understanding of the layer structures and stoichiometry in some of the cases. Why would you use EAG for SIMS analyses? Well, EAG has over 50 SIMS instruments for all type of mass spectrometers designed to do best detection limit or best measurement, and quickest turnaround time. And more importantly, as I was describing to you, SIMS measurement need to be quantified to be meaningful, and getting a reliable information for your epitaxial materials. That requires that you have all the reference materials in the materials that you're measuring. EAG has been selling these reference materials, and it is the industry benchmark for SIMS quantification. At the moment, at EAG, we have 6,000 reference materials that allows us to quantify wide variety of elements and wide variety of matrix species. And I wanted to make a point that for compound semiconductors, properly calibrated ion implant reference materials makes the SIMS data useful. You can measure the dopant and impurities together with the group 3 or group 5 atom fractions. So it is useful for dopant design or troubleshooting. You have to have very high sensitivity for low concentrations, especially in gallium nitride materials, and that requires a special SIMS protocols. Now, unfortunately, we don't have a silver bullet in SIMS method that gives you everything you see here in one measurement. You have to have a very specific designed SIMS measurement to be able to address all the questions you will have. And before I end, I would like to acknowledge my colleagues who contributed to this webinar. We owe Jeff Surface, Özgür Çelik, Mike Salmon, and Wei Zhao, and more importantly, Charles McGee, mentor to all of us in SIMS quantification, who has been answering the questions, I assume, throughout the webinar, and he will be the one who will be giving me other questions. So just to give you an idea of EAG, we have 600 highly educated employees, more than half are PhDs. We do services in 50 different countries, and we in a given time we work with 4,000 clients. That we have 20 different lab locations. The ones that are pointing is where the SIMS laboratories are, even though they could be far away from where you are. We are only a FedEx or UPS or a USPS delivery service, or 12 hours away from shipping to any one of you. Why would you use EAG? There are several reasons, but I think it is important to state right at the top that the client confidentiality is core to our business. We are a global leader for materials testing services with broad range of instruments and expertise that leaves us poised to take on even most challenging materials engineering related issues. And just to let you know, through the pandemic, EAG had stayed open because we were considered essential business, specifically for medical materials analyses and defense industry analyses. And the best way to get in touch and find out how we can help you is going into our website, eag.com/contact.